Hello, everyone. Thank you for your interest in this talk, and welcome to my talk about functional programming inside OOP. It's possible with Python. Here we're going to run into some concepts and facts about functional programming, and my goal is to raise some curiosity about these topics and make the world a better place. First of all, let me introduce myself. I've been a software engineer at Stack Builders for more than 3 years. Currently, I'm working on a project as one of the tech leads with Python and some React applications. Besides that, I collaborate with community engagement by organizing Github and the Meetup and more events like last year at Oktoberfest. Feel free to connect me on LinkedIn and check out my past blog posts. In my personal life, I practice Kendo, Iaido, both Japanese martial arts. I'm a photography enthusiast and regularly post interesting ones on my Instagram account. I don't consider myself a functional programming expert, but I worked with languages such as TypeScript, Ruby, Java, C, PHP in the past, and currently play a bit with Clojure and Haskell. As stack builders, there are a lot of Haskellers from whom I have learned a lot. We use functional programming patterns in hybrid languages. For the record, I haven't used a for loop in a while, the pun intended. So why functional programming? To me, it has made my life easier. So let me explain some of the reasons. Compared with imperative programming, functional programming solves the problems in an easier and efficient way by focusing on the what rather than how, which is the declarative programming way. Divide and conquer by focusing on the implementation of smaller and testable pieces, also known as functions. It makes the debugging process easier, which takes around 80% of the development time according to the recent memes, and makes our code simpler, which compiles with the Zen of Python. The code will be easier to test also, and I will elaborate more on this at the end of the agenda. In a blog post from 2009, our friend Github and Rosum wrote about the origins of Python's functional features. Although he made functions first-class objects in the first place, he didn't design Python as a functional programming language. However, due to its popularity, the users wanted to do more with lists and functions. So they started to implement their own map function and use a hacky way to build anonymous functions. Then, in 1994, the higher order functions map, filter, and reduce were included in the standard library, along with the lambda expressions. Naming variables is hard, right? So imagine naming expressions when building a programming language. The term lambda led to unintended consequences, causing the users to compare the syntax to other programming languages and raise more issues about the lack of advanced features in Python. Lisp programmers can get a clear idea of this issue. Lambda expressions didn't have the reference to the outer scope. This was added in version 2.2. And from then, it remembers the reference from the outer scope. Is that concept familiar to you? I'm asking. So if you're thinking about closures, you're right. This is an essential feature of functional languages. Nowadays, the fans of Lisp comprehensions are larger, and the all higher functions, syntax, and lambda expressions too. Reduce was moved to the functools package, but this is still encouraged to study its syntax to learn how things work under the hood and the motivations behind them. Github and Rosum said in this blog post or article named "The Fate of Reduce in Python 3000," not having the choice streamlines the thought process. Okay, so am I already convincing you? Let's walk through the most important features of functional programming that I frequently use on Python. Take this example from Django source code from 13 years ago. Compare with this latest version, which is this one. The implementation migrated from an imperative design using loops and comprehensions with mappings and filterings In the bottom of the presentation, you can see the link that goes directly to the source. Okay, immutability. An immutable object is an object whose state cannot be modified after it is created. Python manages the mutability of objects differently. Booleans, strings, and integers are immutable objects, but lists and dictionaries are mutable objects. What is the benefit of having immutable objects? We have thread safety. No matter which thread is accessing the object, it is guaranteed to have the same state it originally had. Also, in object orientation, we have better encapsulation. We can trust that our objects won't change when passing them to other methods. And they can always be passed as reference, so we won't need to use complex techniques for copying objects. Since the objects don't change, it's easier to track down the causes for some bugs, making our debugging process more efficient. Let's say we implement this function that adds something to an object. An element to a list and some integer to a value, like this in this example. So it is natural to think that after the execution of any of those functions, the value will be affected. That's true only for the one that manipulates the list. The list is a mutable structure. If we inspect the ID of the value for the mutated object, we confirm that it's the same object. A different behavior happens for the integer value. Let's print more information for introspection. A different object is assigned to a value inside the function scope, and it is returned, so it didn't affect the original foo value. Okay, so let's move on into decorators. So many of you might be familiar with this feature. This adds functionality to an existing function. This is also part of metaprogramming because one part of your code is being modified by another at compile time. Decorators were born because of the higher order functions. Instead of creating new functions, we just get an existing function, execute it, and extend the implementation inside a new one. It's a function being called inside another function wrapper. In short, a decorator uses closures. Let's see this example. We initially define a function that increments a number +1. Next, we define and return a decorator double increment, which applies a function to it and receives and does some extra logic. Finally, we use the syntactic sugar using the add symbol to apply this decorator function. If we do some introspection into the Python's compile code, we can still find our original function inside the closure object. We can even invoke it with the original parameters and get the result for the original one. Let's review about partial application of functions. So this feature is incredibly useful when we need to reduce the number of arguments that any function takes. Let's take a look at this easy example, as always. We have a function getURL that takes 2 arguments, the URL to be fetched and some user role. But instead of calling it with a repetitive role, we can simply call it as a new function with a known role. In this case, we create using the partial function that is included in the functools package and pass it the first argument, the role argument. Let's see another example. In this case, we define functions that will match strings against known regular expressions. For example, the regular expression for an email pattern or the regular expression for the URL pattern. We simply use the partial and the match function and get a simple function that can be reused every time. Okay, lazy evaluation. It's an evaluation strategy that holds the evaluation of an expression until the value is finally needed. This concept was also prevents repetitive evaluations. The lazy evaluation was introduced in lambda calculus around 1971. With lazy evaluation, we can define infinite data structures and reduce the memory footprint because the values are created only when they are needed. In Python, we can make use of it by using the generators, for example. A generator is just a function that uses the yield keyword. And just by using it, the execution will stop at this point and resume it whenever we need to generate a new value with this same function. Take this another example. Did you know that opening a file, reading each of its lines, yields also a generator? I learned this. This is something new that I learned while I was trying to make these slides. Fun fact. The line variable is assigned to the lines in the generator f in this case. Okay, so type annotations. My favorite feature in Python. Last year, I presented an entire talk about type annotations in Python. And to sum up, type annotations can help us to detect bugs at development time and increase the readability and maintainability of our code. Have you noticed that all of my code samples have type annotations? It's hard. It is hard for me to write code without types. I currently use this feature in a production project, and recently it has become more popular among open source developers to provide type hints or APIs. In a recent presentation, let me share this. In a recent presentation, Github and Rostum said that type annotations feature is still growing. And it has learned some things from other languages, such as TypeScript. The type checking tools are now easier to use and integrate in your favorite editor. You have no excuses for not using them. So get your cameras ready or make a screenshot of this slide until it's published and check out the article that I wrote last year about the type annotations in Python or my talk at PyCon China 2020, where I did an entire presentation about this topic. Well, structural pattern matching. This is an interesting one. So Python 3.10, the newest one, includes structural pattern matching. If you have used, for example, C or JavaScript, maybe you're familiar with the switch statement. Well, the difference here is that it is used for comparison between an object or expression and a literal. In contrast, Python design is a declarative approach that uses the type and the shape of the subject. Of course, we can use or match a literal, but it can also match patterns with values, classes, unpacking, nesting, and even we can use the if guards, conditional guards. Let's see, it's more easy to understand with an example. So given a point, which is a tuple with two values, we can implement our match logic. For example, by the way, this is the syntax, match the point and use case. We can match the logic for the following cases or points. In the case of 0, 0, in the case of 0, y, in the case of x, 0, in the case of x and y. Actually, there are two cases for x and y. The difference is in the first one, we can use an if guard to just to print something different. And finally, a wildcard. The underscore is called wildcard in this feature, which is a value that doesn't match any of the above patterns. The underscore behaves as a wildcard and not as a default case as in the previous programming languages that I mentioned before, for example, JavaScript. Also, it can be used as a part of a complex unpacking. Let's see this another example. Well, in this case, we are matching a tuple with 3 values. As you can see, test variable is a tuple, and we do some unpacking in any of these cases or pattern matchings. Finally, this last case uses a wildcard that matches any value that can be here, and this is why we put it at the end of our logic. Same as we do with other programming languages, such as Haskell, for example. Okay. That was all about the features that are included natively in Python. So let's see another functional programming patterns that Python doesn't include, but we can implement it. The first one is currying. Currying transforms a function that takes many arguments into a function that accepts just one argument and returns a function that takes fewer arguments. This is a key pattern of many functional programming languages. I won't go deeper into details since I'm not an expert in this topic, but as a quick overview, I can say that besides styling preferences, it's a way to save some state inside pure functions. So having functions with partial arguments applied and reduced expensive computations. So the theory of currying it's a bit long and hard to understand at first sight. For example, if a function f sub n takes n arguments, then you can turn it into a function c sub n, which takes one argument and returns a function c sub n minus 1 that takes n minus 1 argument and has access to the arguments that was passed to c sub n. What? Okay, let's see. Let's see with examples, which is better. Let's start with this function that just sums up 5 values. A, B, C, D, and E, and returns the sum. We can convert that as a function that takes only one argument and returns functions with partial application of its arguments. It's kind of ugly, right? Well, at the end, we can use this will be equivalent, passing the 5 arguments, the file numbers to the function, that having this new function that takes just one argument, or returns a function that takes another argument, and so on. What about having something like this? Just a decorator that is easy to use, but sadly, it's not included in Python. But we don't have to reinvent the wheel. So in this section, at the end, I can share my slides, but you can see in this blog post that it's a reference where there's a neat implementation of currying as a Python decorator, something like this. Okay, let's see about composition. Remember when in Linux or any Unix-based systems, we do something like this. For example, print out the contents of a file, and then with this output, just apply another function to filter out these lines with this content. Well, you know that this bar character or operator is called pipe, and it gets the result of the previous executions and passes as an argument to the next one. So composition is a similar concept, but with the reverse order of functions executions. It allows to build more sophisticated functions out of simpler ones in an easy and a readable way. There are programming languages such as Haskell where composition is part of its core, and you can do something like this easily. Just compose two functions by this operator. But there's a non-native way to do function composition in Python. If you need to compose two functions, you can write something like this, right? Just write a function that gets two arguments, which are functions, and returns just the arguments like you do in mathematics, nested. But what if we have an undefined number of functions? We can write a piece of code that looks like this. What happened here? Seems complex at the beginning. We use reduce, or with the name of most functional programming languages, name is fold, to iterate and accumulate the application of a list of functions into a single one. So we do this unpacking of the arguments. Well, compose is now a variadic function that takes many functions as a tuple, unpack them, and iterate using reduce, and apply all these functions in order. We can use it like this. Let's say we have 3 functions for the typical HTML tags for making a table. Then we can build a new function with a composition of these 3 in order. See, you can use compose and pass the order is important here. So you can pass these functions in order. And when you call this function, that is now the composed one, with something, the first function is applied, then the second, then the third. Okay, let's see about monads. As I said before, there are a lot of functional patterns that we can implement in Python. Monads is an interesting one. I will try to explain because it was kind of difficult for me to understand, but I will do my best. Okay, so they have a reputation of being difficult to understand, to be honest. I'm not sure if I fully understand them. But why we can use the monads? Because this structure allows adding context to values. Think of them as a boxed value. Another benefit is that we can chain or pipe existing functions by taking the advantage of the monad structure properties, which I won't cover in this talk because they're really well documented. But this is a simple Haskell example where we want to declare a function that returns a value or 0 for a maybe monad that holds an integer value. As with the previous topics, monads are not supported by Python, but it's possible to implement this design pattern. For example, like this. This implementation seems quite long, isn't it? But let's break down a bit. We start by defining a simple class that holds a value, this value. We build this constructor first. Okay. The first method, unit, just wraps the value into a maybe monad, returns the object with the class monad, maybe monad. And the nothing method also returns a maybe monad with an empty value. The magic happens here in the bind method. See, okay. Finally, we override the representation. I will explain this later. But we override the representation. This is a magic method representation to see how it can just print out in the console for introspection. Testing this logic, we can wrap integers as values as monets. If you wrap a non-value, it returns a nothing value. Chaining methods are just passing the function as arguments. They will be binded in order. For example, 1000 will be converted into a string, and through that, it will get the length of that string, just for. Let's review a bit, again, the implementation of the bind method. Well, the basic of the monad is that if value is known, you can return the same value, but you can also apply this binded function into the internal value of the monad and always return an instance of the monad. We are just checking that the result is part of is an instance of the main monads. We can return it right away, or just wrap it out again. But it always has to return a maybe monad, as you can see in the type annotation. Let's see another example. This is an interesting one. We need to calculate a conversion rate. Here there are two helper functions. One that formats the value as a percentage, and the other that calculates the ratio. Only just a division between count and the total number of clicks in this case. So first, we build from them new functions that accept only one argument. So these functions can be bindable or composable. We need them to be changed with our monadic structure. See, in this case, we have the ratio clicks. Apply this get ratio function with a static value of 70. And also we create this percent function as a partial application between multiplying, which is part of the standard library of Python. We have this operator module where we can use the multiplication operation, and the first argument, 100. Now, if we bind these functions in the order we need, we can get the result that we want. If some of the functions return a null value, it will be passed to the rest of the chain. Let's see what happened here. First, we create wrap the value, the conversions integer value into a maybe monad, and then start binding functions. Ratio clicks that we implemented in the previous slide, the percentage function, a round function, a string function, and the format function, just to get the 43% formatted in the way that we wanted. If any of these functions fails, in quotes, for example, passing a non-value, we won't get an exception or error in the middle. We only just get a non-value passed between all the chain and get nothing at the end. Maybe monad with a nothing value. Remember that we override the OR operator. Let's go back to see. Here, this is a magic method just to override the OR operator in this function. And what are we implementing here is just call the bind method that is part of the class with an F function. So with that definition, we can have a simpler syntax for chaining. See, in this case, we're using just the pipe, just a Linux style. Pretty cool, huh? Now the last part is about testing. So let's start with a quote that Joe Eames wrote, which is, "Code that is hard to test, it is not a good code." If you use TDD, test-driven development, or WTA, write tests after, you know that tests are an important part of our daily projects. Writing pure and small functions with no side effects simplifies a lot the complexity of writing tests. Our code will become portable, reusable, predictable, and easy to test. Using an imperative approach to write our test, we'll need to do everything in all steps, create mocks in order, or otherwise the flow will break and explode. But in this declarative paradigm, which is stateless, we don't need to care about the order of the big picture of our logic, just our isolated and pure functions. The outcome of a function is dependent only on the input and nothing else. I couldn't find the author of this one. But here's another interesting quote. Object orientation makes code understandable by encapsulating the moving parts, but functional programming makes code understandable by minimizing the moving parts. Michael Feathers wrote this one. So the moving parts are state mutations. We won't deal with them in functional programming, as OOP does, with encapsulating them. We reached the end of our journey, but not of the road. I hope that you feel curious about this concept related to functional programming and why they will make your life easier, at least your programmer's life. There are a lot of interesting features in Python in the Funtus model, so please check out the official documentation of this model and play with them a bit. As you can see, Python is something like a hybrid language. It is designed to be object-oriented, but with an interesting set of functional programming tools. You can mix and improve the way you write your logic. And of course, learning pure functional languages will change your mindset with the long term. All the references are included in my presentation, which I share. If you have any questions, feedback, suggestions, feel free to reach out or connect with me. So thank you for your time and attention.